So what I'm introducing today is the topic of digital signatures. So in the text, this is chapter 4. And the point of a digital signature is to verify if you get a message that the message is really from the person or the organization that claims to have sent it. So the document you're getting is not secret, but you want to know that it's authentic. So the problem is how to authenticate a received document, D. So in this chapter, the sender is someone named Samantha, and she's sending some document to Bob. But Bob wants to know for sure that the document really came from Samantha. So the text gives a nice example of a situation in which this is important. Suppose you are updating some software and you get a software update, which you have to put into your computer. But you really need to know that the software update comes from the company that made the software, and it's not someone sending you a bogus so-called update that will compromise your computer in some way. So how do you authenticate that the document you received really is from the person who's supposed to have sent it? So it's like, for example, you get a document from someone, and how do you know it's from that person? Well, maybe it's because they signed it and you recognize their signature. Right? So it's not so much that the document is secret, it's not, but you need to know that it's an authentic document. So how can you check that the person or the organization that purported to send you the document really did so, right? So what we need is some sort of system where there is a public key, and anyone who gets a document can use the public key to determine whether it really has been signed, whether it was really sent by the person who claims to have sent it. Okay. So we want a signature procedure, right? So that's the idea. We want so what we want is a digital signature scheme. And this guy is going to involve several steps. So we have a document D. So this is the digital document to be signed. And so we need some algorithm, a signing algorithm. So the document is put through the signing algorithm process, and you get DC. This is like the signature or the signed document. So this is not the document, this is the digital signature. So you will be sending, along with the document, the signature. And the signing algorithm that has to be something which the person sending knows how to do, but no one else knows how to do. So there is some private key that the sender uses, pay private, that's the private key. So the sender has some secret way of signing a document, right? And it's private, only the sender knows how to do this, okay? And so this is the signing part of the digital signature scheme, right? You have a document that you want to be signed, so you need to send a signature. So you have a way to sign the document. So this is the signature on the document. You've changed the document. This is the signed document. And the receiver has some way to verify that the signature is authentic. And anyone can verify a signature. There's a public key that allows you to do this, public. So there's some public key that allows you to verify. So what goes into this verification algorithm? So there is the document, and that's the document, and the signature. Right? So you have a document that you want to send out, and you want people to be able to verify that it really is you who sent the document. The document's not secret, but you want people to trust the document that you sent it. So along with the document, you send your signature. So everyone in the world can get the document and can get your signature, but how do they know it's truly your signature? So there's some verification algorithm. There's some public key that you can apply to the document and the signature to check that it's really your signature. And the output of this is either the statement true, which means the signature is valid, or false. This means the signature is valid, and false otherwise. So your verification algorithm has to be able to tell you whether or not it really has come from you, whether it's your signature on there and not someone else's who forged the signature. Okay. So we're no longer sending a secret document that we don't want someone else to intercept. Document is public, but we want people to know that it's authentic. And in many cases, having a reliable digital signature algorithm is as or more important than having a good crypto system. In many cases, the message being sent is not secret, but you have to be able to believe that it really is a valid message. It really comes from the sender and not from someone trying to mess up your system by sending you something that will corrupt the system if you use it. Okay. Any questions about this? So this is the idea behind a digital signature scheme. And there are several. In particular, I'm only going to discuss one. One is enough for our purposes, just to understand the nature of these things. The text gives one based on the RSA public key crypto system, and another based on the El Gamal public key crypto system. And I'm going to show you the RSA digital signature scheme. Okay. So again, this is chapter 4 in the text. So this is the RSA digital signature scheme. So Samantha is going to send a document D to Bob, but she wants Bob to believe, to verify that she sent it and no one else. So what Samantha does is choose. So Samantha chooses two large secret prime numbers, P and Q, and she multiplies them. And she publishes N, this number N. So what is put in the public domain are going to be two things. The first is the number N, and then she does the following. So, and she publishes N, but because of the difficulty of factoring, the enemy, Eve, is not able to find P and Q because Eve cannot factor N. Factoring is hard. Knowing N as a product of two primes doesn't let you compute the two primes. So this is the first thing Eve does. The second, so this is step one. Step two, Eve chooses an integer E such that, now of course E knows P and Q. So E therefore knows P minus 1 and Q minus 1, and she knows how to multiply them together. And Eve chooses a number E such that the greatest common divisor of E and P minus 1, Q minus 1 is 1, right? And again, E is secret. Sorry, E is not secret. She's going to publish E. So what is made public is E, N, and E. So these two numbers are put in the public domain. But because E knows P minus 1, Q minus 1, Eve can compute a number D such that D times E is congruent to 1 modulo P minus 1, Q minus 1. So this is very important. This is one reason why this was a question on the midterm exam. If a number E is relatively prime to a modulus, it has an inverse, a multiplicative inverse. The V is relatively prime to P minus 1, Q minus 1, which is how you chose E. You can find a D such that DE is congruent to 1 mod P and Q. Right? So Samantha has a document D, and she wants to add her signature. And what is the signature? You sign document D by computing D, capital D, to your secret exponent little d mod n. And that is what we call the signature. Okay. So everyone in the world knows capital N and capital E. And Samantha is going to send Bob a message, D. And she doesn't, and anyone can know D. There's nothing secret about D. The important thing is to know for sure that it really is Samantha who is sending this message, D. So she signs it, and her signature is S. So Samantha, along with the document, sends S. So there are two items being sent to Bob, a document D and a signature S. And Bob has to verify the signature is valid. So the verification scheme is the following. So this is the verification method. Bob computes S, the signature, raised to this public key E, and computes it modulo N. All right. So Bob has N, Bob has E. He computes, he gets D and S. He takes S and raises it to the power E. And if S to the E equals D, then Bob knows that the signature is valid. Okay. Now, why would this be the case? So if the signature is valid, then S is congruent to D to the power D mod N, and that implies that S to the E is D to the power DE mod N. But because DE is congruent to 1 mod P minus 1 Q minus 1, this is congruent to D mod N by Euler's theorem. Euler's theorem says that if D and N are relatively prime, then D to the P minus 1 Q minus 1 is congruent to 1 modulo PQ. And I should say, just to emphasize this, D, we choose D to be in the range between 1 and N. Or you choose N to be bigger than D. That's the, you choose P and Q so that P times Q is bigger than D. Right? And that's it. Now, how could someone take Samantha's signature? How do you get this S? You get this S by raising the document D to the secret number little d. How do you get little d? D has to satisfy the congruence DE congruent to 1 mod P minus 1 Q minus 1. So you know E, you know N. You can get D if you know P minus 1 Q minus 1, but you don't know that. You would know this if you could factor N to find P and Q, but factoring is hard. Factoring cannot be done. So you cannot get P and Q. So you cannot get D. So you cannot compute the S, for which S to the E is congruent to D. Another way of saying that is, you're given D, you're given N, you want to find a number S such that S to the E is congruent to D mod N. How do you do that? You don't know how to do that. Unless you know P and Q. So let me do a numerical example of this. And see what goes on. So this is an example of the RSA digital signature. So we have Samantha, who chooses two secret primes. Say one is 1223 and the other is 1987. And then she multiplies them together, 1223 times 1987. Let's see, I'm going to do this in Maple, because I like Maple. Let's see, where's my Maple? Coming up slowly. So let me share screen with my Maple for a second. So N is going to be the number 1223 times 1987. Oops. So N is 2430101. So 2,430,101. Eve chooses, so Eve chooses. Then she chooses a number E. She chooses the number 948,047. And this has to have the property that the GCD of E and P minus 1, Q minus 1 is equal to 1. So let me calculate that. Let me go back to my Let me go back to my Maple. So in this, I should have defined P. P was equal to 1223, and Q was equal to 1987. And my N, just to double check, was P times Q. Yeah. So what is P minus 1, Q minus 1? So P minus 1 times Q minus 1. Oops. We got the time sign. Let me put that in there. P minus 1, Q minus 1 is 2,426,892. And I want the greatest common divisor. And what is E? Let's see. E was equal to 948. 0.047. So the integer greatest common divisor of E and P minus 1 times Q minus 1 is 1. So Eve made a good choice, or Samantha made a good choice. So the greatest common divisor of E, 948047, and P minus 1, Q minus 1 is 1. So what is being published? The numbers being published are N and E. The secret number that Samantha has to calculate is the number D, such that D times E is congruent to 1 mod P minus 1, Q minus 1. And a number little d with this property that Samantha finds is 1,051,235. Let's just check that this is correct. Let me go back to Maple. So that's my E. D is supposed to equal 1,051,235. And if I take D times E, oops, D times E minus 1, that I want DE to be congruent to 1 mod P minus 1, Q minus 1. So the integer remainder, IREM, the integer remainder of this number, DE minus 1, when divided by P minus 1 times Q minus 1.
Professor, we cannot see that.
Oh, I'm sorry. Let me share the screen with this. Thank you.
Thank you.
So this is D, and I want DE to be congruent to 1 modulo P minus 1, Q minus 1. So I multiply D times E, I subtract 1. I divide by P minus 1, Q minus 1, and I want the remainder to be 0. Ah, it is 0. So good. All we know is that the numbers in the text are reliable. So DE is congruent to 1 mod P minus 1, Q minus 1. So D is the secret number that only Samantha knows. Okay. So then Samantha has a document. A document is going to be a number between 1 and N. So between 1 and 2,430,000. So the document that is going to be 1,070,777. So this number is between 1 and N. That's fine. So what is the signature? The signature S is going to be the document raised to the power D reduced mod N. Okay. This is the algorithm for constructing the signature. So let me see if Maple can do this. I actually have no idea whether it can deal with these numbers. So let me go back to Maple. Share the screen. So instead of using the letter D, which in Maple stands for a derivative, so I can't use it, I'll use a different letter instead of D. I'll call it capital M. So the message I want to sign is 1,070,777. And I'm interested in, and my little d. So here is D, here is M, here is N. I have all those numbers. So I want to know what is the remainder, what is the congruence class of M to the power D when I divide it by N. So this says S is 153,337. Let me stop the share. Oops. Wait a minute. I didn't share that right now. So this was my M. That's my message, but in the text is capital D. This is D, the secret exponent. So I take M to the D mod N, and I get 1,153,337. And good. That's exactly what the text got. So what does Samantha send? Actually, they're using Victor for the recipient. Victor is the name of the guy getting the messages. What Samantha sends to Victor is the number D, that's the message, and the signature S. What is already in the public domain for everyone to use is the number N and the number E. So what does Victor do? Victor computes S to the power E mod N. So everyone knows N and E, right? These are public keys. Everyone knows N and E. Victor gets D and S. He wants to know that the message really came from Samantha. So he takes S to the E mod N. And if S to the E is congruent to D mod N, then the signature is truly true. The signature really came from Samantha. So let me actually see if I can calculate this in Maple. Let me go back to my Maple. Share screen. Oops. Cancel that for a second. Share screen. Okay. So this M to the D, where's D to the D in the notation of the text mod M. That's my S. So I want to calculate what is S to the power E mod N. So I want the integer remainder of S to the power E modulo N. And if this is equal to the message, I know that it's really Samantha's signature. Oops. Ah, it's equal to M. So the signature is valid. Yeah. Okay. So that is one digital signature scheme. Okay. So it's just a few pages in the text, but it's important to understand this. Okay, any questions about this? Any questions about anything else that we've done up to this point? So the three new bits of cryptography we did yesterday and today were the Vigenère cipher, which is a classical Renaissance era cipher, the knapsack problem, subset sum problems, which are very interesting and important, and this digital signature scheme. So this is what is covered in the several homeworks that I posted. I want to make sure everyone knows that the first revision I did yesterday of the homework, the edition of the book that came up was the first edition. So later in the day, I changed the assignment because I wanted everything to come from the second edition. So you would have gotten the second email yesterday with the revised homework assignments. Okay. Any questions about any of that? That's all I wanted to do today. Sorry.
Yeah, Professor, this is not for encryption, decryption, or just for signature valid or invalid checking?
Just for the validity or just to determine whether or not there is a true correct signature.
Okay.
It's not. So in this case, the message is public. So the message D is public. The question is whether this is verifiable, whether it's true. As in the example I gave. So let's say you're using Microsoft Word and you get an email from Microsoft that says there's an upgrade, click on this and we'll upgrade your software. And you want to know whether it really did come from Microsoft. Well, you're not going to do anything because the software has already been developed, built in, but there will be some signature verification scheme that comes with the purported upgrade. So your computer knows that this is really a reliable upgrade. And it's not someone, sitting in Moscow trying to get a hold of your computer for nefarious purposes, right? So
we can check the digital certificate on the top of the address bar. If we click the address bar, it says like digital certificate is valid.
I'm not sure what you're asking. Are you saying?
If you want to check signature is valid or not from any website, you go to computer, you go to the address bar, and there is a clock sign. You click on that, and that is written. You can see that digital certificate is valid.
No kidding.
Or
So I don't know any of this. I just know the theory of the mathematical theory of cryptography. So you're saying that. So where do you find this?
Oh, you go to address bar in the URL. When you type URL,
right,
you see a clock sign, any website.
Mm-hmm.
If you click the clock sign, you can see the connection is secure or not, digital certificate is valid or not.
Oh, so after we log off, I'll try that because
Okay.
that's really interesting. That's the advantage of having computer science students in this course.
Yeah.
That's good. Thank you.
Thank you. Thank you.
Okay. That's all I'm going to do today. Very likely before Monday, I will post another lecture on YouTube. I just have to decide which of various possible topics I want to add. But that's all we're doing for today. And there's some homework using this RSA digital signature scheme that you should try. Okay.
Thank
And
you.
I'm online at 7 o'clock tonight if there are any questions about any of the theory or the homework that we've done or that's assigned.
Professor,
Yes.
please don't forget about the final review.
Oh, I'll send out a final review this weekend.
Okay, thank you.
Yes.
Thank you.
But sorry, just to be safe, if you haven't gotten one by in your email by Sunday morning, send me an email to remind me.
Okay.
Okay. All right.
All
Good.
right. I will.
Okay. Thank you. All right. Bye all.
Thank you.